Okay, I hope you hear me well. If not, you should tell me. And it's a pleasure to be here. And it was also a pleasure to be here already in the morning. It's a reflection meeting celebrating the birthday of Alon and Yuval. Happy birthday. Let me thank the organizers for the invitation. Thank you all for coming, and thank also the remote participants whom I don't, I see a few of you, so thank you also for participating. So the title is The Polynomial Method. And what I mean by this is a very simple, basic result in algebraic geometry that has lots of implications in combinatorics, in graph theory, in number theory, and in geometry. And I'll try to describe some of these. Now, this is a survey lecture. Many of the results will be old, but many of them will also be very recent. And if there are any questions, I'm not sure if I see the chat here, but you can try to unmute yourself and ask questions, or we'll have time for questions at the end. So let me start by telling you what I mean by this basic result. So I start by reminding you Hilbert's Wilson results, one of the foundational results in algebraic geometry. And it just says that if we have an algebraically closed field and we have the ring of polynomials over the field with n variables, then if some polynomial in this ring vanishes over all the common roots of an ideal, then it belongs to the radical. Or saying it more explicitly, if we have this polynomial f of x1 up to xn, and we have m other polynomials generating an ideal g1 up to gn, then if whenever all the gi vanish, so does f, then some power of f is a linear combination with polynomial coefficients of the polynomials gi. Now I want to look at a special case where the gi's are actually univariate polynomials, m equals n, gi is a polynomial only in xi, and it has all its roots in the field. In this case, we can say a bit more, so we don't have to assume anymore that f is an algebraically closed field, it is just a field, and we have these sets of roots, S1, S2, up to Sn, which are subsets of the field f, and the polynomial gi of xi is a product of x minus s, as s belongs to si. So just a polynomial that has distinct roots in the field. Now, if f vanishes whenever all the gi do, so this is just a complicated way, if you want, to say that f vanishes over the box S1 times S2 times and so on times Sn, but it's written this way to see that this is really a case of Hilbert's Wilson results. Then f itself, and not a power of f here, is a linear combination with polynomial coefficients of the gi. And moreover, we have some control on the degrees of the coefficients, namely each product, hi times gi, the total degree of it is at most the degree of f. So this is a statement. And by equating the highest degree part of the right-hand side and the left-hand side, we can get the following, which will be more convenient to apply, and this is what I want to call combinatorial rules, and that. So it says that if again we have a field, we have a multivariate polynomial f over the field, and we have some non-negative integers, t1 up to tn. We assume that the total degree of f is c1 plus c2 plus and so on plus cn. And let me stress that this is the total degree of f. We don't assume that the degree in xi is ti. So this the degree in xi can be bigger, but just the total degree of each monomial is not more than the sum of the ti's. Now, if we also know that the coefficient of the product of xi to the ti is non-zero, then whenever we have subsets of the field, S1 up to Sn, and the size of Si is bigger than Ti, so it's at least Ti plus 1, then F cannot vanish over the whole books. Namely, we can find little Si and capital Si, so that if we substitute them in F, we get non-zero. This has to be a small size here. Okay, so this statement, and you see that the case n equals 1, a univariate polynomial, just the trivial or the well-known fact that a non-zero univariate polynomial cannot have more roots than its degree. Right? So this is a multivariate statement of the same thing. And I want to show you some consequences of this, and I also want to mention some intriguing problems. So one statement that I wanted to make before it is to say that usually when we apply these combinatorial notions as to prove some statements, the proofs obtained are non-constructive in the sense that they do not provide efficient procedures for solving the corresponding algorithmic problems. Often there would be corresponding algorithmic problems, and some of the questions I want to mention are the algorithmic problems or variants of each of these statements, and trying to find an efficient algorithm. So I'll show you some simple results or consequences of this, and I'll show some very simple proofs, and then I'll try to tell you something about some more complicated proofs. So here is the first statement. This is a special case of something more general that was conjectured by Hunter Snevely and was eventually proved by Bodan Arsovsky. But I'm telling just a special case. In this special case, you can say a little bit more. It's a statement in additive number theory, if you want. So if you have a prime P, and you have a sequence, so K will be some number less than P, and we have a sequence, A1 up to AK in ZP, in the finite tree with 3 elements, or the integers module P. They do not have to be necessarily distinct. And we have another set, subset B, also of size K, of ZP. Then the claim is that always there is a numbering of elements of B. So I number them by B1 up to Bk, and we can number them in such a way, suppose the sums AI plus BI will be pairwise distinct in ZP. So that's a claim, and I want to show you a very short proof of it. So just a few lines using this statement that I said. So we define the polynomial that you see here. It's a polynomial with k variables, and it's a product of van der Monde times a product of the difference of xi plus ai minus xk minus aj. And you see this polynomial we chosen so that if we substitute now elements from B for each xi, and we get something that is non-zero, then because these things are non-zero, it will mean that the xi's are pairwise distinct, and therefore they just give you a numbering of elements of B. And because this part is non-zero, then the xi plus ai is always different than xj plus aj. So this is the statement that we want. So we just want to apply this combinatorial notion that with the field being Zp, Ti is k-1 for every I. You see the total degree of this polynomial is a product of two terms each of degree k choose 2. So the total degree here is k times k-1, which is the sum of all the Ti's, and Si will be B for all I. So if we know that we will be able to apply it, and for this we have to check that some coefficient is non-zero. If the relevant coefficient is non-zero, then there is a substitution from B that makes it non-zero, and as I explained, this means that it gives us a numbering of elements of B as needed. Right. Now, what about this coefficient? So here, actually, it's very simple to check this coefficient. If you want, it's also a very special case of the Dyson conjecture, where all the terms are 1, for those that know the statement of Dyson conjecture, but you just can open the Van der Waals determinant. So let me look at the polynomial again. If you want here a coefficient of highest degree, you cannot use any of the AIs or AJ. So it will just be the square of Van der Waals. And if you just expand it and write it as a sum of k factorial terms, then you will see that this coefficient that we care about is exactly k factorial, and because k is less than p, p is a prime, then this is non-zero in the field Cp, and this gives what's needed. And it's not surprising that one can get some extensions by using the full Dyson conjecture, and there are some other variants and other extensions. So this is one example of a very simple proof, and here is an algorithmic question that I said I want to mention some of those. Suppose you are given this sequence A1 up to AK, and you are given a subset of Zp of cardinality k, then you know by this statement that there is a number of elements of B, so the total sums Ai plus Bi are pairwise distinct. Can we find efficiently such a number? I mean, the proof was because some coefficient of some polynomial is non-zero. Of course, it is not even algorithm. Can we actually find such a number? Okay. So this was the first example. Let me give you another one, which is also very simple. So I call it a permanent lemma. And it looks like similar to the very basic result in linear algebra that says that when a determinant of an n by n matrix is non-zero, then for every vector of free coefficients, there is a unique solution. So what we will do here is that we will replace a determinant by permanent, in equal by not equal, but I'll explain what I mean by not equal. And we'll also insist that we want a solution in 0, 1 with each xi being 0, 1. So here is the statement. We have an n by n matrix over field. The permanent now of this matrix is non-zero over this field. And B is some vector of free coefficients. So then the statement is that there is an x which is 0 or 1 in each coordinate, and the ith entry of A times X is not equal to Bi for every I. So we replace the determinant by permanent we replaced equality by inequality, where inequality is understood as not being equal in each and every coordinate, and we insist that the solution is a binary solution. Okay? And again, the proof is just 2 lines, 3 lines, I guess here. So we apply this Mulchten's to the following polynomial. So again, it's a product of terms. The ith term is a term that will ensure, if the value of the polynomial is non-zero, it will ensure that the ith entry of a times x is not equal to bi. And we apply it with all the ti's being 1, with si being 0, 1. And we have to observe that the coefficient here of the product of xi is the permanent. So this is non-zero by assumption. We could have replaced, and this is the point proof. So we could have replaced si by any set of cardinality 2. Let me mention some maybe entertaining application of this. Suppose we have a bipartite graph with classes of vertices A and B, each of size n. And this bipartite graph has a perfect matching. So you see an example here of such a bipartite graph. And suppose that for each element of B, we have some integer, d1, d2, up to d3, which we denote for big degrees. Then the claim is that there is a subset X of A, so that the number of neighbors of each vertex Vi of B in this set X is not Di. And in the examples that you see here, then you see that I could choose X to be the red vertices. We wanted this degree, red degree, to be non-zero, so we have to choose this. Then we wanted this degree to be different than 1, so we have to choose this. And then the third one is already okay. So the degree is different than 2. And the claim is that we can always do it. And you see that this is just the statement of the permanent lemma, as I said, right? Just applied to the adjacency matrix of the graph. And again, you can ask yourself the algorithmic problem. This one, I think it may be simpler, so I didn't think about it too much, but again, I don't know to do it without algebra. So suppose you get a bipartite graph with a perfect matching, and you get these forbidden degrees, d1 up to dn. You know that there is a subset X of A, so that the degree of the ith vertex of B in X is not Di. Can you find such a set efficiently? It's not clear. Maybe it will be interesting. Let me tell you something about a slightly more sophisticated proof. So this has to do with graph coloring, and I want to define some extension of the usual chromatic number of a graph. This was a definition given independently by Wissing and by Erbesch, Rubin, and Taylor in the 70s. So it's called the least chromatic number of a graph G. And this is defined as a minimum number K, so that whenever you give a list of K colors to each vertex of the graph, there is always a proper coloring, the coloring which any two adjacent vertices get the same colors, assigning to each vertex a color from its class. So if all the color classes are the same, this is usual coloring, but here it's more general, so we allow a general sense. And the definition clearly implies that the least chromatic number of every graph is at least a chromatic number, but in fact, very strict inequality is possible. And indeed, it is known that every graph in which the average degree is big has big least chromatic number. So if one of these parameters tends to infinity, also the other one tends to infinity, and of course you can have bipartite graphs with chromatic number 2, in which the degrees are very big. So each such graph will have a large least chromatic number. So in general, the least chromatic number can be much bigger than the chromatic number. Now we want to apply something to some polynomials, and here is the relevant polynomial here. It was introduced by Sylvester and by Peterson in the 19th century. They were motivated by some questions in invariant theory. And actually, it's interesting to note that some of the terminology of graph theory came from these things that were motivated by invariant theory. So maybe you wondered why a perfect matching in a graph is called a one factor. What is a factor here? So this is really a reason, because it's some divisor of some polynomial. Okay. But anyway, so here is the polynomial they defined. It's more or less the simplest polynomial that you can associate with a graph. You associate every vertex, say, with a variable. So I denote here the vertices by 1 to n, and vertex I, the corresponding variable is xi. And now what we do is just we take the product of xi minus xj over all edges ij. The sign does not matter much, but I wrote here that we take always I, s, and j, just to be specific. So this is the graph polynomial. Now note that this polynomial, although this was not their motivation, but this polynomial is very convenient when we are dealing with coloring problems. Why? Because if we have sets S1, S2 up to Sn, and each of them is a list of colors, but we can think, of course, of list of colors as really, we can represent them by real numbers or by complex numbers. And then there are some little si, capital Si, so that when I substitute them in the polynomial, I get non-zero, if and only if there is a proper coloring of the graph assigning to each vertex a color from its list, right? This is obvious by definition, because if this is non-zero, it means that each of these terms is non-zero, namely xi, the value it got, is different from xj for every 2 adjacent vertices, which is exactly a proper color. So this indeed calls for using this combinatorial notion that you see, even the notation is the same as I used. The conclusion was that f of S1 up to Sn is not zero, right? So we should be able to say something using this. Here is actually, I should apologize, by the way, that the original presentation was PowerPoint, but I was asked to convert it to PDF, so I lost the little animation that I had, and therefore we always get here full slides, but you are encouraged to think where you would add animation if you could. But anyway, so here is one statement that follows from this observation. So by the first version of this combinatorial notion that I mentioned, a graph G is not 3 colorable if and only this graph polynomial Fg is a linear combination with polynomial coefficients over the complex field, let's say, of the polynomials xi cubed minus 1, right? Just because those have roots which are the 3 roots of unity, and therefore the graph is not 3 colorable if whenever we substitute cube roots of unity for all the vertices, the graph polynomial will vanish, right? Because we have only 3 cube roots of unity, and because of the statement, this holds. Right? So I wrote here as an exercise, it's an easy exercise, to use this fact to prove that K4 is not free-correlable, so we write van der Waal determinant corresponding to this K4, and you expand it and you see that it gives you this expression. But I wrote here in remarks that this does not prove that NP is equal to co-NP. Now, I'm not going to talk much about complexity classes, but and one reason that this does not prove is that if it would have proved, then probably I would give a different title to the lecture. But you see, it looks as if it more or less proves it, right? Because this looks like something that enables me to convince you that the graph is not free-correlable. And this problem is co-NP hard, so if I could have convinced you quickly, then this would show something. But the trouble is that although this statement holds, I cannot really show you this certificate that shows that the graph is not free-correlable, because maybe, for example, the polynomial hi would be too long. I'll not be able to tell you the description of them in polynomial time. But still, this should be useful, the fact that a statement like this holds. Let me get back to least following. So again, by the version of this combinatorial that I mentioned, if G has k times n edges, the total degree of the graph polynomial was the number of edges. So if it has kn edges, and the coefficient of product of xi to the k in this graph polynomial is non-zero, then it would tell us that the least chromatic number of the graph is at most k plus 1. So we should just plug it in this in the statement of the combinatorial notion that, and then this is what it would tell us, right? The conclusion was that for every set S1 up to Sn of size at least k plus 1 here, it could be there is a choice of Si from capital Si, which corresponds to the corollary, so that the graph polynomial is not zero, meaning that this is a proper corollary. So this kind of follows immediately. And this is a good thing because in general it's very hard to prove that a graph, the least chromatic number of it is of k plus 1. You would think that you have to go over all possible lists of size k plus 1, and indeed it is known that deciding if the least chromatic number of the graph is at most some given number is what is called pi 2 hard, so it's a bit higher in the polynomial time hierarchy than being NP hard. So in general it's hard, but this gives us some sufficient condition. And some long time ago with Nick Darcy, we interpreted this coefficient in the graph polynomial combinatorially in terms of some Eulerian orientation or Eulerian subgraphs in some orientation of the graph. So it is possible to do that. And this was useful to prove several segments, in particular, to solve some questions in the original paper of Erdős, Rubin, and Taylor. But what I want to tell you is how this can be used to prove a strengthening of the four-column theorem. So the four-column theorem is a best known result in graph coloring, probably the best known result in combinatorics in general. And actually, those of you who have been here in the morning in the lecture of Gil Harari, one thing that he mentioned was that it is known, this was actually proved by Tate, again in the 19th century, that the four-column theorem, which was conjectured by Francis Guthrie, was proved by Abel Haken, and later by Robertson, Sanders, Seymour, and Thomas, and as probably all of you know, the proofs still use a lot of computation, and there is no kind of traditional proof. In fact, the second proof by Robertson, Sanders, Simon, and Thomas uses even more computer than the first proof. So it uses for the two mean steps, whereas Abel-Haken uses it only for one of the steps. But this four-quarter theorem is equivalent to the fact that the chromatic number of the line graph of any cubic breathless planar graph is 3. So there are lots of buzzwords here, but it just means that we can call, if we have a planar graph and every degree of this planar graph is exactly 3, then we can color the edges by 3 colors. We are coloring edges now, so that every 2 adjacent edges get distinct colors. And bridgeless means that every edge is contained in a cycle. Okay? So it's pretty simple to show that this is equivalent to the four-quarter theorem. And as I said, this was proved by Tate. It's one of the early papers that gave the wrong proof to the four-quarter theorem, but part of this wrong proof was correct, and this part was correct and interesting. So the following statement is therefore stronger than the four-quarter theorem. This is something proved with Shishé and Tarsi, and the same was proved independently by Elingham and Godin, who actually proved some extension for planar multigraphs as well. And what this says is that the least chromatic number of the line graph of any cubic radius planar graph is 3. Not only can we color the edges by 3 colors with adjacent edges getting distinct colors, but we can do it from this also. Now, of course, it would have been nice, and this was what we hoped at the beginning, if this would give a kind of an algebraic proof of the four-quarter theorem, which is not need computers, but unfortunate but still interesting fact, I think, is that the proof uses the four-quarter theorem, so really it reduces this more general segment to the segment of the, or to Tate's version of the four-quarter theorem. But since the proof is strange, or the reduction is strange in the sense that it shows that so to apply this polynomial method, the main thing is to show that some relevant coefficient is non-zero. So we can interpret this relevant coefficient combinatorially, as I said, and in the case of planar graphs, of line graphs, of cubic breathless planar graphs, you can show that actually this coefficient here counts proper 3 colorings of the edges of the cubic graph, and this number of proper 3 colorings is non-zero by the four-quarter theorem. So it is a reduction, but the reduction is strange. I mean, it uses the four-quarter theorem to conclude that some coefficient is non-zero, and because of this, some graph is colorable. And again, this raises the corresponding algorithmic question. I should say that although the proof of the proofs of the four-quarter theorem are long, complicated, make heavy use of computer computation, still they do produce very efficient algorithms to 4-color planar graph, and therefore to 3-color the line graph of any cubic breathless planar graph. But here again, we don't know the algorithm because the proof comes with this polynomial coefficient. So suppose you are given a large cubic planar breathless graph, like the one you see here, only larger, and for each edge you get a list of 3 colors. We know that you can color the edges properly by assigning each edge a color from its list. Can you actually find such a color efficiently? We don't know. Okay, let me talk about some.
Noga, may I ask about slide 14 before you go to the next topic?
Yeah, so sure, you can ask, but I didn't hear. So what's the question?
So slide 14. So on the left-hand side, should you have a power of the graph polynomial since you're using CN1 and not CN2?
Oh, so this is CN1, not Hilbert's Muscheln-Satz, but the first version of the combinatorial Muscheln-Satz. And in that first version, the main thing was, or one thing was that the polynomial appeared in power 1. And also we knew something about the degrees of each HI. Okay?
Okay, thank you.
Thanks. Okay, let me talk briefly about some more recent result with Raimundo Briseno, Nishan Chagotia, Alexandro Marzino, and Simon Spinka, whom you see here. And that's a problem about coloring that is motivated by statistical physics. So I just say some relevant buzzwords. We want to consider colorings of the graph of the d-dimensional lattice, which is a bipartite 2D regular infinite graph, by Q colors. And let me just say that the relevant buzzwords here, which are not so important for understanding what I want to say in the next 2 or 3 minutes, that the proper Q colorings of this graph represent a zero temperature antiferromagnetic Q states Potts model. For instance, okay, so we are considering this these colorings. And suppose we have 2 proper colorings of this infinite graphs, and denoted them by F1 and F2. Both of them are colorings by Q colors, they are proper. And suppose that we have 2 sets A and B, which may be finite or infinite. There are 2 subsets of ZB, but they are far from each other. So the distance between them is at least some function of the dimension. In the question, which is kind of natural because of this motivation, has to do with mixing properties of such colorings, can we always ensure that there is one proper vertex coloring of this graph that coincides with the first coloring on A and coincides with the second coloring on B? So it kind of merges them. And the answer is that so this is what we proved in that paper with which Marzino and Spinka. The answer is yes if Q is at least D plus 2, and no if Q is at most D plus 1. Now this picture is kind of an explanation why it is not true when Q is only D plus 1. But let me not talk much about it because I see that my time is limited and there are a few things that I still want to be able to say. And for the more interesting part, if Q is at least D plus 2, and we want to show that for any 2 colorings, F1 and F2, there is a coloring that agrees with F1 and A and agrees with F2 and B. So the first observation is that it's enough to show that when we have a sufficiently large box, d-dimensional box, n times n times n, d times n zt, and we have some proper coloring of part of its boundary, then we can extend it to the interior, to proper coloring of the interior. And indeed, this is because we can partition the grid into such boxes, color the ones that intersect A according to F1, the ones that intersect B according to F2, and because A and B are far, then no box will intersect both of them. And then we can complete the coloring box by box, and whenever we reach a new box, then only part of the boundary of it is this color, and we have to extend it. So we have to prove this thing. And then the observation is this is a statement about least coloring, because we can just assign to each vertex in the interior of a box the set of all colors besides those that appear on its neighbors that are already colored. So this is some statement about least coloring, and then it turns out that we can apply the polynomial method with combining it with Hall theorem to prove that some orientation of the relevant graph exists. This orientation will tell us that the relevant coefficient is not zero, and this is because the graph here is bipartite. So once you have something that contributes to this coefficient, then it will be non-zero. Now I realize that it's impossible to follow much here, but at least you get a flavor of things. Maybe okay, how much time do I still have?
I think about 10 minutes late, so I think you have about 10 minutes more.
About 10 minutes, okay. So let me remember something quickly about that. So this is a hat guessing game that was considered by Fanning, my partner here. And instead of reading it, let me show you the picture. This is together with pictures of my co-authors on this, Umri Ben Eliezer, Tzachi Kamu, and Chong Changwan. And this starts with a long puzzle. So suppose we have n people, each of them has a hat on its head, and the hat can come in n possible colors, and you look at the color of your neighbors, and then you guess what is the color of your hat. And as a group, the group wins if at least one of them guesses correctly. And the claim is that for this case of a complete graph, then the group can always do it because the ith player guesses the color of his head according to the assumption that the sum modulo I of the head colors, the sum modulo n of the colors of the head is I. The sum has to be something, and this player will win. And if I know the sum of the heads modulo n, and I see the colors of all the other heads besides my own, then I can compute my own. And then people considered the same question for general graphs. So now we have a graph. Each one sees only the heads of the colors of the heads of his neighbors on the graph. We have a player on each vertex and has to guess his own color. And a complete bipartite graph looks interesting. And there are some known results about small complete bipartite graphs. There were some questions about this. And the only thing I wanted to mention here is that for complete bipartite graph K11 or K22, there are always optimal guessing schemes that are linear. Always they are similar to the one I described for the complete graph. My guess about the color of my head is a linear function of the colors that I see. And one thing that can be shown, and this is in our paper, is that already if the number of colors is 4, then for arbitrarily large bipartite graphs, there are no linear guessing schemes that will work, although with nonlinear guessing schemes, they will work even if the number of colors is roughly square root 10. And maybe I'll just say that the proof that with linear guessing schemes, you cannot win, again, define some polynomial and sees that in this head guessing game, the guesses are winning guesses, even only if this polynomial does not vanish, And to show that this polynomial always does not vanish for some assignment, you again can use a version of this combinatorial illusion that, and from Q equals 4, you can use the fact that in characteristic 2, determinant and permanent are the same. Again, I don't want to say much about this. There is the proof is somehow written here. I just mentioned that this is closely related to some old conjecture we had with Chechet and Tarski, that if we have a non-singular n by n matrix over a field with at least 5 elements, then there is always a vector with non-zero, so that its image under this matrix also has non-zeros. So we could prove it to non-prime fields. This is quite similar to what is being used in this head guessing game. And there is a very recent result by Janusz Nudge and Peter Pach with a later variant together with Esteban Pumon also, that shows that this conjecture holds also for all large primes, all primes that are bigger than 61, besides possibly 79. And again, there is a natural algorithmic problem here, and again, we don't have an efficient solution for the natural algorithmic problem. Let me say quickly something about the geometric application. So again, starting from an old result with Zoltan Foredy, what we showed, this was a question of Shuni, and we showed that if you are in the n-dimensional Euclidean space and you have all the 2 to the n binary vectors, the vertices of say a unit cube, and you want to cover all of them besides the origin by hyperplanes, then you need at least n hyperplanes. You can do it in many ways, using n hyperplane, for example, with all the hyperplanes x I equals 1. And so this is, or some, okay, so this one way. And the proof, again, is an easy implication of this combinatorial illusion that say, now there is an extension of a question by Clifton and Wang, and they asked what happens if we want every point to be covered k times, and the origin is still uncovered. And they have an example showing that n plus k choose 2 hyperplanes always suffice, and they conjecture that this is the truth. They could prove this conjecture for a k equals a 2 and 3, and they got some lower bound for every bigger k. And this was recently improved lower bound by Lisa Sauerman and Yuval Victor. They got an improved lower bound, but I'm mentioning it mostly because of the method. So the methods here use some versions of this combinatorial illusion that, but in extensions, or extensions of it that work for polynomials that vanish to high order. And in particular, in this paper by Sauerman and Yuval Victor, they got a tight version of this statement for polynomials that vanish to high order on the cube besides the origin. And this is used on manipulations. This is proved by manipulations with polynomials together with some properties of the Catalan numbers. Quite interesting. And actually, extensions of this type of this combinatorial illusion that appeared before by Bohr and Serra, by all these papers that you see here, even before the ones by Clifford and Wang and by Sauer and Microphone, and these are again some extensions that are interesting to study. And here also there is a natural algorithm problem that we don't know to solve efficiently. I use 2 more minutes, so I wanted to say something about the hardness. So many of the questions I mentioned were algorithm questions, and one may wonder if indeed these algorithm questions are hard. And one way to prove hardness is to show that some problems are what is called complete for some natural complexity classes. Now, as I said, I will not talk about complexity classes. Usually when you say that you are not going to talk about something, it's exactly before you are going to talk about it, but let me only say one sentence about it. So the relevant complexity classes here appear to be PPA and PPAD. These are 2 complexity classes defined by Christos Papadimitriou. PPA stands for polynomial parity arguments, and the D is for directed. And you may wonder if some of these algorithm problems are complete for these complexity classes. These are complexity classes that always have solutions, and they deal with the difficulty of finding solutions. So I don't want to show anything about this, but here is some proposition. So the following algorithmic problem, which is kind of the algorithmic problem corresponding to the combinatorial enrichment as it is. So this is hard. If the case is hard as inverting one-way permutations, like, for example, computing discrete logarithms in big fields, so which are believed to be hard. There are some cryptographic protocols based on this assumption. So suppose you are given an arithmetic circuit, and it's computing a polynomial in n variables over a field. This field can be even the binary field. And by looking at this circuit, you see that the degree is a sum of TIs for some TIs. In my case, all the TIs will be 1. And you also see by looking at the circuit that the coefficient of the product of xi to the TI is non-zero. And now you are given sets Si of size Ti plus 1. We know that there always is a solution, little psi, capital Psi, so that if we substitute them in the polynomial, it's not 0, but can we find one? So as I said, if we can, then we can also solve discrete log. So it's unlikely that we will be able to do this efficiently. Still, it looks natural to suspect that the specific problems that I mentioned, like distinct sums for billion degrees, this following the choice version of the four-quarter theorem, head guessing, cube mean covering, and actually these are several errors. Each of them may be simpler. And it's interesting to know if indeed they are. And with this, I finish. Thank you.
Okay, thank you very much. We have time for a short question or two. If there are any question here, you can ask.
Yeah,
if there's a question from home.
Right. So if there are questions from home, you can unmute yourself and ask, or you can. So as I said, I see very few of you, but I see, for example, Peter Winkler here. Any question, Peter? Okay.
Okay. If not, then I have a small question regarding the antiferromagnetic Potts model. Is there some boundary on the number of different columns that can be found?
Right. So let me repeat it for the people. So the question was, in this thing I mentioned about the anti-ferromagnetic Potts model, if there is some bound for the number of colorings that can be obtained from this, and actually the proof would give some pretty big lower bound, an exponential lower bound for the number of ways of extending coloring. It will not be completely tight, but it will be nearly tight if you take a logarithm, I think once, but if, yeah. So for the logarithm, it gives an essentially tight same one.
Entropy is understood. Any other questions?
If we have a general planar graph, then can we say something about the least coloring number of it?
Yeah, right. So the question was if we know something about the least coloring of a general planar graph. So actually this has been studied a lot, and it's known that every planar graph is five least colorable. So the least coloring of a planar graph cannot be more than 5, and this is tight. It can be 5. And so this was proved by Carsten Thomassen. And there is a proof also, this proof was combinatorial, but there is also a proof by shooting Zhu using this polynomial approach. In general, for planar graphs, the least coloring is always shifted by 1. So for example, the least coloring of every bipartite planar graph is at most 3, although the chromatic number is 2. And this we proved in this paper with Tarsis. It was also once a question of Erdish, Rubin, Taylor. Similarly, the least chromatic number of any triangle-free planar graph is at most 4, whereas for a without least it is 3, and again it is tight. So it looks like for vertex coloring it is shifted by 1, but for edge coloring we know that it stays the same.
Thank you.
Anyone else? Okay, so let's thank the speaker again. Okay, so we'll reconvene at 5:50 in 7 minutes. Okay, so we'll reconvene in about 7 minutes.